All right, so continuing on with galvanic cells, concentration cells are a galvanic cell that has identical electrodes. So if the electrodes are made of the same element, then they both have the same reduction potential. One of them is going to get oxidized and one of them is going to get reduced. And so what that means is that your standard E cell, your standard potential for your cell, is going to be 0 because one of those values is going to be positive and one of those values is going to be negative. So what makes it work is that the cells are going to have different ion concentrations. And so we're going to get a small amount of voltage as we work towards equilibrium, but it's all due to the different ion concentrations in the two half cells. The electrons are going to flow from the lower concentration, the anode, to the higher concentration at the cathode. Remember that electrons flow from anode to cathode. The cell potential is just calculated from this equation that we were using before, our Nernst equation, but this value here is going to be 0, so it's all due to the Q. So our products to reactants ratio. If our reactants are bigger than our products, so this is the bottom term, the denominator, and here's our numerator. So if our denominator is bigger, then Q is going to be small. And remember that that was the extra push. So that means that we can use that to our advantage to make E, our measured cell potential, larger than our standard cell potential, which again, this value is going to be 0. So in order for Q to be small, our anode concentration for the products must be dilute compared to the concentrated cathode concentration. So here is a picture of a concentration cell. Here they're using copper as both of the electrodes. This concentration at the anode is smaller, 0.1 versus 2 at the cathode. Remember that this concentration is going to be increasing because the metal is going to be coming off into the solution to form copper 2+. And here we're going to be decreasing this concentration. Our copper 2+ is going to be plating onto the cathode. So the anode is more dilute because this cell's concentration will increase. The cathode is more concentrated. This cell's concentration will decrease. Or I should say this half cell. This concentration will increase over time, and this half cell concentration will decrease over time. All right, so a galvanic cell is constructed using 2 copper electrodes. Compartment A contains a 0.015 molar solution of copper 2+, and compartment B contains 2.5 molar solution of copper 2+. Our first question is to identify the anode and the cathode concentrations. So for Q to be small, we want it to be the more dilute concentration on top over the higher number. So, and these are both going to be 1 coefficient. So first of all, let's maybe write our equation out. This might seem silly because it's going to be the same thing on both sides, but I think it'll help. It helps me visually. So we're going to have copper and copper ions turning into copper ions plus copper. All right, so in this one here, we are losing electrons. So this is oxidation. This is what's going to happen at the anode. And then for this one, we are gaining electrons. So this is reduction, and that's going to happen at the cathode. And remember, if we want Q to be small, Q is going to equal our products over reactants. So Q is going to be anode over cathode. And we want Q to be less than 1. Okay, so we need to put 0.015 over 2.5, which means that compartment A is going to be the anode. So anode will be compartment A, and the cathode will be compartment B. Calculate the cell potential at 298 Kelvin. So our equation is E equals standard minus RT over NF, natural log of Q. Remember that this is 0, so E is going to be equal to 8.314 times 298. We're going to transfer 2 electrons, and then Faraday is 96,485. Natural log of 0.015 over 2.5. So we should get a small voltage. We should get a measured voltage of 0.066 volts. And then write the cell notation. So the cell notation is we're going to write what's happening. We're going to focus on the half reaction of what's happening at the anode first. So our anode is, we wrote that above, is going to be copper to copper 2 plus. And we are not at standard solutions. We're not at standard conditions. So we want to go ahead and put in the concentrations. We're not at 1 molar. So this concentration is going to be 0.015 molar at the anode. And then we're going to do 2 lines for our salt bridge. And then we're going to write what's happening at the cathode. So the cathode is starting out with copper 2 plus in a 2.5 molar solution, phase boundary. And then we're going to copper solid. So there is our cell notation. And this E is positive. Make sure we write that. So that is, those are concentration cells. All right, a little challenge here, electrochemistry and KSP. A student sets up a concentration cell at 298 Kelvin using 2 lead electrodes. So right off the bat, we know we have 2 lead electrodes. And so our standard cell potential is going to be 0. Compartment A has a solution of 0.10 molar lead-2 nitrate, and compartment B has a saturated solution of lead-2 iodide in contact with excess solid. The measured cell potential is 0.0567 volts, and the student observes that the electrode in compartment B acts as the anode. So we don't know the concentration of compartment B. We just know it's saturated. Lead iodide is not a very soluble compound. It makes a precipitate. So our concentration is going to be pretty low. If that's acting as the anode, we know that it's going to be lower than 0.1. And we know that our measured cell potential is 0.0567, and our standard cell potential is 0 volts. It says calculate the concentration of the lead in the saturated solution in compartment B. So we know that that's the anode, so that's going to be the one on top of our Q expression. So E is going to be 0.0567. That's going to be equal to the standard cell potential, which is 0. So I'm not going to write that one. And then we're going to do the negative R, 8.314. We are at 298 Kelvin. 298 Kelvin. We're forming lead-2. So 2 electrons transferred, 96,485. Natural log of x over 0.1. Okay, so if you rearrange all of that to solve for x, we should get a concentration of 0.0012 molar. And then it says calculate the KSP for lead-2 iodide. So we know the solubility in a saturated solution, which means that we are at, this solution has as much dissolved as it can, which means that solution is at equilibrium for KSP, for the solubility product. And so if we look at the dissolution or the dissociation of the ions in lead-2 iodide, we're going to get in equilibrium, we're going to have Pb2 plus 2I minus. And so the solubility of those is going to be S, and this will be 2S. And so our KSP is going to be equal to S times 2S squared, which is going to be equal to 4S cubed. And so what is S? S is our molar solubility. And we know that the S is going to be this number because this is the solubility. This is the molar solubility of lead in the solution. And then because it is lead to iodide, the iodine is just going to be 2 times this. And so when we're calculating KSP, we're going to do 4 times this number cubed. So 4 times that number cubed is going to be 6.9 times 10 to the negative 9. That is our KSP value. Moving on to current and charge, we have a new equation here. So I equals Q over T. This is on your equation sheet. I is current in amps or amperes, sometimes also just an A. Amps is also the same as coulombs per second. Q is charge in coulombs, and then T is time in seconds. So be careful, watch the time, because sometimes they'll give you time in minutes or hours, and you'll need to make sure that you convert to seconds before you can use amperes as a conversion factor, or if you calculate amperes. Make sure that you are watching the time units. Remember that Faraday's constant is 96,485 coulombs per mole of electrons. So if we know the charge and the time run, or the amps and the time run and the elements involved, we know how many electrons are being transferred. We can use that to calculate the mass of our electrodes, what either is gained at the cathode or lost at the anode. If we know the mass and the current, we can determine how long the cell will run. If we know the time and the mass of the electrode, we can determine the amount of current required or given, depending on the type of cell that we have, if it's galvanic or electrolytic. So there's all kinds of things we can do with this equation and with stoichiometry to combine these into some very, very good problems. So here we have a practice problem. A voltaic cell. So voltaic, we know that it is spontaneous, constructed using magnesium and silver. So we looked at this one earlier. These are the reduction potentials. The cell is powering a 0.5 amp light bulb. How long in hours can this battery power the light bulb before the magnesium anode of 2.45 grams runs out? So for problem A, we know the mass of the anode is 2.45 grams. And we know that that's magnesium. So we can go to moles of magnesium using the molar mass, which is 24.31 grams of magnesium per mole of magnesium. We know that for every mole of magnesium, we're going to transfer 2 moles of electrons. 1 mole of magnesium. There we go. 2 moles of electrons. We know the charge of a mole of electrons because of Faraday's constant. And now we know that we're powering a 0.5 amp light bulb. Remember that that is the same as coulombs per second. And so that number is going to go on the bottom, 0.5 coulombs per 1 second. And they want to know in hours. So how many seconds are in an hour? If you do 60 times 60, you're going to get 3,600 seconds per 1 hour. So if you type all of that in, multiplying across the top, dividing the bottom, you should get 10.8 hours. That's how long we could power that light bulb continuously before we run out of magnesium. All right, B, if the cell runs for an hour, how much will the mass of the silver electrode increase? So now we're going to go backwards where they're giving us the time, and they also want to know about the other electrode. They want to know about silver. So we're running for 1 hour. So 1 hour is, we just did this a second ago, 1 hour is going to be 3,600 seconds. We know that we have a 0.5 amp light bulb, which is 0.5 coulombs per 1 second. So 0.5 on the top and 1 second on the bottom. We also know the charge for a mole. We know the coulombs for a mole of electrons is Faraday's number, Faraday's constant, 96,485 coulombs per 1 mole of electrons. For silver, we know that for every mole of silver, we are transferring 1 mole of electrons. Making sure that our units are canceling. And then a mole of silver, we know the mass. They're asking about the mass, so we're going to need the molar mass is 107.87 grams per mole of silver. So if we do that, if we let the cell run for an hour, at 0.5 amps, our silver electrode should increase by a mass of 2.01 grams. Okay, so that leads us on to electrolysis. That is the end of this section.